Welcome back, welcome back. We're heading for the one-way repeated measure design, but first let's step back for a moment. Way back in Chapter 7, we looked at the independent groups design, 2 independent groups of participants, 2 levels of this single IV, for example, pen versus laptop, and the effect size of interest that corresponded with our research question was just the difference between these 2 means. And of course, we displayed it on this difference axis with its confidence interval, and we interpreted that effect size and its confidence interval. Then we extended this, independent groups, still 1 IV, but with 3 levels. And so the Bushman study, we had 3 independent groups, and we could specify, preferably planned in advance, any comparison of 2 means we were interested in that corresponded with our research question, and again display the effect size, the size of that comparison, the estimate of that comparison with the confidence interval, and that's what we'd interpret. And we could click to specify which comparison we wanted to look at, and we would see the corresponding effect size with its confidence interval on a difference axis. Then we could go one step more complex, but still with the same sort of logic, still independent groups and 1 IV, but this time with 6 levels, and we could specify subgroup contrasts. We're still finishing up with a single degree of freedom effect size, and so our effect size we're interested in is, again, the difference between these 2 subset means plotted with its confidence interval on this difference axis, and again that's the effect size and confidence interval that we'll interpret for this particular comparison. For example, Alzheimer's diet mice compared with Alzheimer's freely eating mice. The next step was Chapter 8, where we looked at a repeated measure design, the paired design, the simplest repeated measure design. So we had a single group of participants and we tested them twice, say the pre-test and the post-test. We had a single independent variable, 2 levels, and each participant saw both levels of that IV. And the repeated measure was signalled by these lines joining the points, and by convention the line joining the means of the 2 measures, the pre-test and post-test. And again we have the difference there, the mean of all the paired differences, or the difference between the pre-test mean and post-test mean. That's our effect size, and we put a confidence interval on that. The good news is that quite often in practice there's a reasonably high correlation between pre-test and post-test values, and correspondingly this confidence interval is quite short, so we're estimating the effect size we're interested in quite precisely, and that makes us very happy. Now we want to do a similar extension of this repeated measures design to more than 2 levels. And the example in the chapter is a critical thinking study by Donahue, where a single group of participants were given a pre-test, then some critical thinking training, then post-test, and then a while later follow-up to see how well the gains in critical thinking ability held up over time. So here we have a single independent variable, and it's a repeated measure, and it has 3 levels. Now, analysing this is beyond the scope of Esky and this book, but this picture makes clear that it is a repeated measure design. Each coloured line here corresponds to a single participant, and so I think we've got about 14 participants, and they all give us a pre-test, a post-test, and a follow-up measure. How are we going to analyse this? Well, in broad outline, exactly the same way that we analysed the one-way independent group study examples a little earlier. So we will specify, preferably in advance, a comparison, for example, pre-test versus post-test, and we will select that, and we'd like to analyse it and display it with its confidence interval, and we'll interpret that difference and the confidence interval. And because, well, it looks here as though we have a quite high correlation between all the pre-test and post-test measures, and similarly fairly high between post-test and follow-up measures, it looks like the confidence intervals on those comparisons will be nice and short, shorter than these, and that's terrific news. So we have a sensitive experiment. We could even think of subset contrast. You might want to compare, say, pre-test with the average of post-test and follow-up. So this would be one subset, the pre-test the other subset, and you'd look at the mean of post-test and follow-up compared with pre-test. And that would be your subset contrast, as usual, preferably planned and pre-registered. And that's the way you would investigate what these results tell you about your research questions. Are you getting a pattern here? Specify comparisons and subset contrasts that match your interests, that match your questions, and look at each of those, the estimate of how big that comparison is based on the data, and the confidence interval on that, and that's what you interpret. Exactly right. A very good general strategy. Preferably, we do that in a planned way, and we could do it also in an exploratory way for some speculative, tentative, suggestive conclusions. Well, should we choose a repeated measure design or independent groups? The sorts of considerations are very similar to those we considered back in Chapter 7 and 8, comparing the simple two-group independent groups design with the paired design. In general, paired or repeated measure is quite attractive if it's appropriate, if we can do it, if it's practical, but we have to watch out for carryover effects. Repeated measure may well give us a sensitive design with short confidence intervals on our effect sizes, but there may be carryover effects. It could be that carrying out the pretest practices you on that, and so you'll do a bit better on the post-test just because you've had that practice. And there are various ways we can try to minimize carryover effects. For example, with this repeated testing thing, we might have two forms, parallel forms of the test, and any participant sees either form only once. In some situations, you can counterbalance the order of presentation of the different levels of the independent variable, not, of course, when you're considering pre-test and post-test. Analysis of variance. One of the bits of jargon that's very commonly a big part of the study of students learning about statistical analysis. And I've always been puzzled why it's used so widely when planned contrasts and planned comparisons are usually the best, simplest, clearest way to analyse any of these more complex experiments. Not always. Sometimes ANIMA can have some value, and there are estimation approaches to ANIMA, but the effect size measures are typically hard to understand, hard to really grasp and to express and to interpret. And quite often analysis of variance is carried out just in the NHST world. So the approach is set up a null hypothesis, which says that for every level of an independent variable, the population means are equal. This is referred to as the main effect of that independent variable. In this chapter, we have only a single IV, that's called A in the jargon. So in this Halle-Gappa study, we've got 6 groups, we've got a single IV, and the null hypothesis would say in the population, the means for all these 6 conditions are all the same. And analysis of variance tests that null hypothesis. The test statistic is F, and informally, it's the amount of variability amongst all these group means compared with, divided by, some measure of variability of data within each group pooled over all groups. So if there's lots of variation from group mean to group mean, this suggests that the null hypothesis is untenable, and this is large, so F will be large. So the F statistic, it actually has 2 degrees of freedom, the first one referring to number of group means, so that's number of group means minus 1, so here we have a case where there are 3 group means, and this 38 refers to the degrees of freedom for this variability estimate on the bottom. And large values of F, compared with what we'd expect under the null hypothesis, lead us to reject the null hypothesis. And here we have 4.41, and if we consult tables or software, for these numbers of degrees of freedom, the p-value is 0.02, so that's less than 0.05. We reject the null hypothesis that all these population means are equal, and the more variation we can see between these group means, the more likely we are to get a large value of F, a small value of P, and have statistical significance. The trouble is that even if we do get very clear statistical significance, we don't know where the difference lies. We can look and guess that perhaps it's here or perhaps it's here, but this is an omnibus test. This is an overall test. And quite often the procedure is to follow it up with what are called post hoc tests, which is a little bit like exploration of where differences might lie between these means. I suggest that if you read a statement like this about an f-value and a p-value, then you think of the p in terms of strength of evidence. So this would give us a reasonable amount of evidence, a medium amount of evidence, that there is some real variation between these population means. We can reject the null hypothesis that they're all equal. But my short conclusion is that for most situations, and I suspect for most that you will encounter, certainly in the early days, our approach of planned contrasts and looking at estimates of effect sizes with confidence intervals is the best way to approach the analysis of all these more complex designs.